Welcome to WikiPodcast. Today we're doing a deep dive into something really foundational. It's all about how we understand and, control electricity.
Absolutely. We're talking about voltage, current, and
Oh,
resistance.
that fundamental dance between them.
Exactly. These three and the law that ties them together, Ohm's law, it's genuinely the bedrock. Explains everything from, well, your phone charger right up to the massive power grids.
Right. So our goal here is to unpack these concepts, understand that relationship Ohm's law, and really see how this seemingly simple idea holds up the whole electrical world we live in.
Yeah, the big question is, how is electricity actually governed? How do we measure it? Maybe you've heard these terms, voltage, current, resistance.
Ohm's law itself, maybe.
Right. But what do they really mean? And, crucially, how do they interact? That interaction is key for designing, well, pretty much everything electrical.
We're going to look at the history a bit, the surprising discovery, the pushback the discoverer faced.
Oh, yeah, the resistance to resistance, you could say.
Huh. Exactly. And the physics behind why it works, plus, maybe an analogy to help picture it all.
Sounds good. Let's jump in.
Okay. So when electricity moves through something, a wire, for instance, there are these three main things going on.
Always. You've got voltage first.
Yeah, the sources often call this the electrical driving force or push.
Think of it like water pressure.
Yeah.
Or maybe a height difference, making water flow down a hill. It's that potential difference, that oomph, that gets the charge moving, measured in volts.
Then there's current. That's the actual flow, right? How much charge is moving past a point each second.
Precisely. Measured in amperes, or amps. If voltage is the pressure, current is like the flow rate, how much water is actually moving through the pipe.
And number three, resistance.
The opposition. Like friction in that water pipe. Every material resists current flow to some extent.
High resistance means it's harder for current to get through, assuming the voltage stays the same, measured in ohms.
And the key insight, the thing that connects them all, is Ohm's law.
Which, in its most common form, is just VIR.
Voltage equals current times resistance. Simple as that, mathematically.
So if you increase the voltage, the push across something with a set resistance, you naturally get more current, more flow.
Or keep the voltage constant, but increase the resistance.
The current has to go down. It sets up this really neat direct relationship for materials that, well, obey the law.
And VIR, it's what we call an empirical law. It came straight from observation, from careful experiments.
Not derived from first principles
It
initially.
just works, describing loads of materials across huge ranges of current.
Which makes it kind of wild that when Georg Ohm first published it, mid-1820s?
1825, 1826 for the work,
Yeah.
published in his book in 1827.
It wasn't exactly welcomed with open arms.
Far from it. He was actually inspired by Fourier's work on heat flow, seeing a parallel between heat conduction and electric flow.
Ah, interesting.
He needed stable voltage for his experiments, used thermocouples, not the voltaic piles, which were less reliable, measured current with a galvanometer.
And tested different wires, length, diameter, material.
Meticulously. And he saw this clear proportionality. His original equation was a bit more involved, accounting for his whole setup, but it boiled down to the VIR relationship we know. Total resistance dictates current for a given voltage.
But then came the criticism. The sources say his work was called a web of naked fancies. Ouch.
Imagine discovering something so fundamental and getting that reaction. There's even a story about the Prussian Minister of Education saying Ohm was unworthy to teach science for preaching such heresies.
Wow. Why? Why so much resistance, pardon the pun again, to experimental results?
Well, the sources suggest a big part was the scientific philosophy in Germany back then. There was this strong belief in, pure reason and deduction.
Ah, so deriving things theoretically was seen as superior to just measuring stuff.
Pretty much. Nature was thought to be perfectly ordered, its laws discoverable through thought alone, not messy bench work. So Ohm's whole experimental method ruffled feathers.
So his approach itself was controversial.
That, plus maybe some academic politics, maybe some issues related to his brother Martin. The climate just wasn't right. It really shows how even clear data can be rejected if it doesn't fit the current thinking.
Yeah, scientific progress isn't always straightforward, is it?
Not at all. It took over a decade, into the 1840s, for Ohm's law to really gain traction, especially as others validated it. By the 1850s, with things like the telegraph needing practical rules, it became essential. People realized other ideas, like Barlow's law, just didn't work in reality.
Okay, so it was discovered empirically, faced rejection, then finally got accepted. But for a long time, people used it without fully understanding why it worked deep down inside the material.
Right. The quest for the why really kicked off after J.J. Thomson discovered the electron in 1897,
Suddenly, we knew it was actually carrying the charge in metals.
which led straight to the first big theoretical explanation, the classical Drude model around 1900.
Okay, the Drude model, how does that picture it? Like electrons bouncing around inside the metal?
It's sort of like bees in a box or maybe tiny pinballs. Yeah. A fixed grid of positive ions and these electrons just moving randomly.
Until you apply a voltage.
Exactly.
Yeah.
Voltage creates an electric field, which pushes the electrons, but they keep colliding with the ions, scattering all over the place.
So they don't just shoot straight through.
No, it's chaotic, zigzagging.
Oh.
But between collisions, the field gives them a little nudge, so they gain this tiny average speed in one direction, the drift velocity.
Okay, a slow overall drift despite the chaos.
And Drude showed, using classical physics, that this drift velocity is proportional to the electric field strength, since current is just all these electrons drifting.
Current density ends up being proportional to the field, which is basically Ohm's law.
Bingo. The first decent theoretical justification for VIR.
But science didn't stop there. Quantum mechanics came along.
In the 1920s, yeah. And it changed the picture quite a bit. Well, quantum theory, thanks to people like Sommerfeld and Bloch, showed electrons behave more like waves in a perfect crystal. They don't really collide with the lattice atoms themselves in the simple way Drude thought.
So what causes the resistance then in the quantum view?
It's mainly imperfections. Impurity atoms, defects in the crystal structure, and atoms vibrating because of heat. Those are what scatter the electron waves and impede the flow.
And quantum mechanics also explained why some materials are conductors, others insulators, and some semiconductors.
Exactly. Through band theory, it's about the allowed energy levels for electrons and how easily they can move between them.
But here's the amazing part, right? Even with this completely different quantum picture.
The core result often holds. The average drift velocity still turns out to be proportional to the electric field for many materials under normal conditions.
So current density, J, is proportional to the electric field, E, the microscopic form, JE, where sigma is conductivity.
And that microscopic view explains why resistance depends on the material itself, its resistivity, which is just 1 over sigma, and also its shape, how long and thick the wire is.
You can actually derive the macroscopic VER we measure with a multimeter from that microscopic J.
Yeah, for a simple wire, V is related to E, I is related to J, and the resistance R depends on resistivity, length, and area A as R. Put it all together.
And out pops VIR again. It's beautiful how the micro and macro levels connect.
It shows amazing consistency.
Okay, so we've got the law, the history, the physics explaining it. But how universal is VIR? What are its limits?
Well, it's incredibly useful for most materials, especially metals, under normal conditions. But what's really surprising, based on recent findings, Ohm's law seems to hold up even for silicon wires that are just like 4 atoms wide.
4 atoms? Seriously? That's tiny.
Mind-blowing, right? It works from power grids down to the nanoscale for these ohmic materials.
But it is still an empirical law, an approximation, not like a fundamental law of the universe.
Correct. It's a description of how certain materials behave. And that behavior can change under really strong electric fields, for example. The nice linear V versus I relationship breaks down.
And lots of components just don't follow it at all, right? They're non-ohmic.
Exactly. Diodes are the classic example. They conduct easily one way, block the other. Their resistance, if you calculate 6, is definitely not constant. It changes dramatically with voltage.
So Ohm's law really describes ohmic resistors, things specifically designed to have that constant resistance.
Which we use all the time in circuits. VIR, IVR, RVI. They're just rearrangements of the same idea. You see that little triangle bumper sometimes.
Yeah, cover up the one you want to find.
That's it. And VIR works directly for simple resistor circuits, whether it's steady DC voltage or changing AC voltage. At any single moment in time, VIR holds for the resistor.
But I sense a but coming. What about more complex AC circuits?
Ah, yes. When you add capacitors or inductors into an AC circuit, things get trickier. The simple VIR doesn't quite cut it anymore.
Because those components mess with the timing. The voltage and current waves get out of sync.
Precisely. The current might peak before the voltage or lag behind it. There's a phase difference.
And that's where impedance comes in.
Exactly. Impeders, usually written as V, is like the AC version of resistance. It takes into account both the opposition to current and that phase shift caused by capacitors and inductors.
So you can write V equals ZI for AC.
You can't, but Z isn't just a simple number like R. It includes information about that phase shift, often involves complex numbers in the math, though you don't need the math to get the concept.
Okay, so Z handles the resistance-like part and the phase stuff, and it depends on the AC frequency too, right?
Critically depends on frequency, yes, unlike an ideal resistor's resistance.
Got it. Any other practical things to keep in mind?
Temperature. Resistance changes with temperature. For most conductors, hotter means higher resistance.
And current causes heating, joule heating. So the resistance might not be perfectly constant if a lot of current is flowing and warming things up.
Right. Those early, really precise tests of Ohm's law back in the 1870s, like Maxwell's, had to be super careful about controlling temperature to make sure they were just measuring the electrical effect.
It's really something. This simple VIR, born from experiments, met with skepticism.
Then explained by deep physics.
Works across incredible scales, yet has clear limits and needs generalizing for things like AC circuits with capacitors and inductors.
It's a cornerstone, no doubt about it. Empirical observation, quantum explanation, practical application, known limits, it covers it all.
So think about how this law, discovered through painstaking work and doubted at first, just quietly makes our whole electrical world function. But then, flip it around. What happens when engineers deliberately use things that don't follow VIR? What sorts of electronic magic does that non-ohmic behavior unlock?
That's where things get really interesting with semiconductors and modern electronics.
Thanks for listening. Write us your opinion in the comments on this. What non-ohmic device do you find most fascinating and why?
Subscribe to the channel to help more listeners reach our episodes.
Thank you and have an amazing day.